Okay, so welcome to CS260B, Algorithmic Machine Learning, and I'm Raghu Meka. So I work mainly in theoretical computer science and machine learning, learning theory, really, complexity theory, and algorithms. And today, what I want to do is go over some of the logistics for the class. How are we going to grade? What is the schedule, and so on. More of the tedious stuff in some sense, but it's good to have you all take a look at them. If any of the dates or anything do not work for you, it's not very likely I'll be able to adjust, but do let me know and we can try and do something. Okay. And then we'll go into the actual course content. All right. Okay. So the first thing is all of the lectures will be recorded and and they'll be available on Bruin Learn through the Echo 360 platform. And also, I'll also have a YouTube playlist of all of the Zoom recordings that you can access as well. Okay. And even though the lectures are recorded, there is also some credit for participating in class. Okay. In the sense that you will definitely be able to do better in the exams if you come to the lectures. Okay. So even if it's recorded, treat that mainly as a resource to help yourself to review material than as an alternative to attending lectures. Okay. And I should tell you right from the beginning, if at some point the attendance drops too much because I'm recording the lectures, I'm going to stop. I really don't want to do that because I want it to be a helpful feature. But if when the energy drops in the class, it affects everybody. Okay. I hope it's fair and it's clear. If you have any issues with that, please let me know. I know some people have difficulty coming in for whatever reason, but that should be okay for a few lectures, not for entire class, entire quarter. All right. Okay. And so the main resource or kind of the spot we will use for announcing stuff and accessing information is the class website, which I am writing it down here in my bad handwriting, but you can find it from my web page as well. Okay. It's just algo ML. This is L. Okay. So if you go there, you'll find all of the resources. My office hours are Mondays 2 to 3. And if you have any questions, you can always reach out to me in my email, and I'll also in a moment tell you about the forum that we will use. We have one TVA, Yimeng, but he is for the MSOL students. So if you're part of that section, you can access that. Otherwise, it's fine. And the other resource we'll use a lot is EdStem. And this is for online discussions, class notebooks, solutions, etc. All right. And what does this look like? If you go to, so this is the class website. And if you access here, you'll see everything. One of the things I want to stress is, so there are many students in this class. Majority are from computer science, but we also have students from many different fields, right? But this class is focused on algorithmic stuff. Okay. So if you're not familiar with kind of the algorithmic notation, how to calculate time complexity bounds or something, please look it up and try to be aware of that constraint. Okay. At the same time, we also are going to use linear algebra. Oh my goodness. Okay. That's not what I wanted, but we also need some linear algebra resources. Okay. So for example, you need to know what the dot product between vectors is, how to compute the projection of a vector onto a subspace. Okay, what does it mean to have an orthonormal basis for a subspace and so on, right? And the reason we will use them is because without that, you cannot do any ML. Okay? Most of machine learning, especially the modern stuff, uses all of these operations every which way. Okay. And it's not that hard to pick them up, but if you're not familiar with them, you will have to put in an extra effort because we are not going to cover them in this class, all right? So make sure, the link is broken right now, but I'll fix it as soon as I end this lecture. So there is an assignment 0. It's not to be submitted. Just look at the problems. Make sure you can answer them. If you cannot answer them, be willing to put in the effort, okay, to make yourself familiar with this stuff. All right. All right. Let's see. Okay. So if you look at this, there are 3 sections. One is linear algebra. That is the most that has the most number of problems. You also need some background in probability theory, and finally basic algorithmic stuff. Okay, you need to know what big O notation is. We'll use it everywhere. Okay, you need to know how to calculate time complexity bounds and so on, right? And we'll also use some programming, but this is stuff again. It's expected for this class. Right? So you'll have to be a little bit familiar with some programming platform, be it MATLAB or Python. Okay. All right. So now, okay, that's about the prerequisites. And the lectures, as I said, are recorded. And for every course, for every lecture, if you go to this course notes, you'll see this sort of page. And if you click on it, it'll take you basically to whatever I'm writing in real time. Okay. So you can access it that way. And you'll find all of the course material there. And let's see what else. Okay, exams. We will have 2 exams for the lecture, for the class. One is on May 7th. That is going to be in here for the people taking the class in person. And for people taking the class online, there's a different scheme, which I'll announce separately. Okay. And we'll also have exam 2, which is by university schedule, like the final exam. But it's not really a final exam. The 2 exams are non-cumulative. The first exam covers the first 9 lectures. The second exam covers the remaining. Okay. And for assignments, we will have 4 assignments, lectures 1 through 5. This is the date that each assignment is going to go out. It's due, what lectures it covers. Okay, 1 through 5, 6 to 9. So in some sense, exam 1 is basically the first 2 assignments. Exam 2 is the last 2 assignments, right? But the lectures build on top of each other. So, you'll see that you can't just jump into assignment 3 and 4 if you're not very familiar with what's happened before. Okay. All right. And lastly, we will use, as I said, we'll use this EdSTEM platform. And anyone with a ucla.edu address can register for it. So just go to the class website. If you'll click on, there you go. Yeah, if you click on this here, you'll be able to register for it. Okay. If you don't have a ucla.edu address, then let me know, and I can add you manually. Right. And the reason, the main thing we'll use this for is to have all of the lecture content here. Okay. If you go to, for example, lecture 1, you'll see lecture summary, and you'll also see the video. This is from last year, but it'll be similar. Okay. And we'll also have working notebooks or demos or kind of implementations of our algorithms. All of that will be up here as well. Okay. Any questions about the exams or any of the logistical stuff about the lectures, the course? And all of the assignments will be submitted on Gradescope. Okay. So if you're registered for the class, you'll automatically be added to the corresponding Gradescope version for this lecture, for this class. And the assignments and solutions will have to be submitted there. Okay. And in terms of grading, the assignments, will tend to be a little bit harder, but they will be graded more leniently, right? The idea behind the assignments is for me to kind of, maybe challenge you a little bit in how to think about them, but keep in mind that the grading is going to be very liberal. As long as you make a genuine attempt, you'll almost get full credit, right? But the exams will again be lower level, but the assignments kind of seem very challenging. It's a little bit by design. The expectation is that just try them out. As long as you try them honestly, you'll get almost full credit. Okay. Any other questions about the logistics for the class? If not, I'll jump right into what we're going to discuss. Yeah. How will the waitlist work? Okay, so right now the class is full, and I have a few people who kind of reached out to me before even the waitlist kind of went up, but they couldn't register. But I expect to add almost all of the people who are currently on the waitlist into the class, and maybe a few more. Typically, there are fluctuations in registrations, after the first week. So some people who are already registered would drop out. That would free up more slots. Right now, both the regular class list and the wait list are full. And I still have a lot of other people asking for PTEs. I'll try to accommodate as many as I can. I don't expect there to be more than 50 to 60 students for the class. Okay. Any other questions? All right. So if not, let's jump right into what this class is about. And you'll also see kind of an outline of what we're going to discuss. So roughly there are, 1, 2, 3, 4, 5 parts in the class. The first one is going to be, is going to take up most of our lectures compared to the other things. This is going to be about optimization. So we'll abstract learning as an algorithmic problem, and we'll just focus on that algorithmic problem. Okay. As I'll stress often throughout the course, this is not what machine learning is just. Okay, meaning there's a lot more other stuff that you have to do to get a working system. But this class is about the algorithmic aspects of machine learning. Okay, so that means we're only going to focus on this for the most part. So we'll reduce it to a few algorithmic problems or a few algorithms that have been kind of, the bread and butter of ML models and kind of dig into them. Okay. All right, so we'll have optimization. Even the next 3 lectures, this online learning part is really very closely connected to optimization. It's just optimization in a different constraints. And then PCA, again, is a form of optimization, but it's an important algorithm that gets used everywhere. And then we'll talk about privacy. How can you get algorithmic privacy in machine learning? And lastly, this is kind of a topic that usually changes based on what students want and how we are doing overall in terms of time. Okay. All right. So the first 4 are more kind of have been around for a while. The last topic is usually covers more current things. Okay. All right. So let's get started with the lecture. Okay. As I said, the exams will each have 25 points. The assignments are 50 points total. Okay. All right. So our goal for this is to understand. And let me emphasize understand a handful of core algorithms. Okay. So our goal is going to be to understand a handful of core algorithms that are used in ML. As I said, we're going to skip where do these models come in, how do you collect the data, how do you do any sort of screening before that, and so on. We're not going to focus on it. Okay. We'll allude to some of these things later on because they do go hand in hand. You can't just segment the 2 things separately and say, okay, I'm only going to work on optimization. You only work on making the model, because then you'll come up with a model that I cannot optimize. You have optimization algorithms that I cannot use for my models and so on. Okay. But luckily, that's not been the case. For the most part, we can really do this sort of compartmentalization, at least as a first order bit. Okay. All right. So with that said, For the first lecture, let me at least motivate a little bit about the algorithmic problem that we're going to discuss. Where does it come from and how does it actually connect to machine learning? Okay. So I'm going to contradict myself and talk about this sort of modeling aspect a little bit just for this lecture. Okay. All right. So let's think, what is learning? So, just think of some, when I say, okay, machine learning or what is learning, what sort of applications or what kind of learning models do you think about, or learning problems that you think about? Just name a few, and I'll pick the one that I have in my mind and it fits my narrative. Okay. So tell me a few of these things. In the sessions, what is learning? Like, what do you think of when I say machine learning? Yeah. Sure. Reinforcement learning is one. Although I would say you kind of pick that up much later, right? There's stuff that you usually do before. What else? Yeah? Linear regression, definitely. What else? You can think of supervised learning, right? That's kind of an umbrella term that you might have seen before. Yeah? Clustering, which is, I think of clustering, or many people do, as basically a version of unsupervised learning. Okay, what else? Any other suggestions? Representation learning, which is, again, maybe I would put it under unsupervised learning, but I think it deserves its own bullet point, given how useful it is these days. What else? Yeah, distribution learning is also a good version. Last time I taught the class, we actually did distribution learning and diffusion models. This time we're not doing diffusion models, we're going to do transformers instead, but all of them kind of, come under these things. What else? They're all related. There are also some different things that you might have heard about, but we're not going to cover, like, active learning. Active learning means that, somehow you have a model, you try to identify, okay, I'm not doing well in this case, and then I'm going to go and try and get some data to fix this specific problem that I think I have. Okay, which is how basically kind of we learn, right? You see, okay, you take an assignment or something, you see that I'm struggling with linear regression, I'm going to revise linear regression, right? That's kind of active learning. And something we will also cover is online learning. Right? So online learning means that, even while learning, you have to kind of you have to be able to use the system. Right? You can't just say, I'm going to wait until I learn and then I'll start making predictions. In some models, there's too much of a cost to just wait till the end and then I'll have a very great model. You have to continuously start making predictions and keep on improving yourself if you can. Okay, that's kind of online learning. We'll spend some time on, I would say, this one here and this one here, and a little bit in, maybe supervised and unsupervised. Okay, but the others not so much. Reinforcement learning is kind of connected to online learning, and we will cover one simple model which kind of fits into reinforcement learning. It's a baby version of it. Okay. All right, so this is a lot of ground to cover, but let's start with, I would say, the easiest one to describe formally is supervised learning. Okay, the other ones take a little bit of, I think I would say ingenuity even in how you define. Okay, supervised learning also, requires some ingenuity, but I think it's a little more clear as what you should do. Right? Okay, so let's start with this question, which is how to model supervised learning. Okay, so when I say supervised learning, maybe you heard this term before. If you have, what comes to your mind? If not, we'll actually define it and see how to do it. So that's okay. But if you heard the term or seen it around, what comes to mind when I say supervised learning? Any suggestions? Okay. Yeah. Label data, or think of applications. What sort of applications come to mind? Like labeling pictures, classification, right? I see a picture. Is it a cat or a dog, right? Is it kind of I don't use cat or dog classifiers, but I definitely use plant classifiers. And I see a weird plant in my garden. I take a photo, and it tells me, okay, this is something. Yeah. Prediction too, right? That's kind of like linear regression. Okay. So the way we model it is basically say we have some domain, typically denoted X, and the domain is going to be completely, we should not put too much of a constraint on what the domain can be. Okay, the basic domain, you will translate into some other representation, which is sort of universal. Everything will map into vectors, and then you get embedded into vectors and work with the vectors. But in the beginning, these can be images, this can be text, this can be DNA sequences. Right, so your label data is basically you have people, maybe a few people, they're parts of the DNA sequences, and okay, this person has this specific disease or something like that. Okay, biometric data, sensor data, meaning you have weather stations, they're collecting all kinds of information. That's also some kind of, yeah. And then we have some labels, L. Okay, and these could be literal labels like cats, dogs, alpacas, whatever. I don't know why I thought of alpacas right now, but that's there. And then you can also have numerical information, right? Actual numbers, right? Like score or the weather today, the temperature, and so on. Okay. You can also have, imagine if your data is like text, you can say a label could be the sentiment associated with that specific text. Okay. So far, this is very generic. You have some domain X and some labels L, and in this domain and labels, we have some data set. And in supervised learning, we imagine we are given this data set. Okay. We are not going to worry about where this data set came from. Do you have to do something? No, we're just going to say that we are given this data set. And so it's not an easy problem often, but we're going to assume we are given this data set. Okay, so here each xi is from your domain, and each yi is a label. Okay, so I have a picture, and it has a label, which is a cat. Maybe here in another data set, it could be just DNA sequences and then labels corresponding to whether or not that person has this specific risk factor, or maybe you also have a numerical score associated with that DNA sequence and so on. Okay, and this is what is often called training data, especially in unsupervised learning. When you are supervised, in supervised learning, sorry. When you're unsupervised learning, it's different. Okay. All right. And given this data set, what is our goal? So in supervised learning, you're given a data set x1 through y1. You can do whatever you want with it for now, let's say. Often there are time, memory and other constraints, but let's put that aside. I'll tell you, okay, do whatever you want with it. And then after that, what is your goal? The goal on almost all of these applications is prediction. Okay? Meaning, we are given a new x from the domain. We want to predict a label for it. Okay. So for instance, you have a database of images with labels, and now I give you a new image, and you have to tell me what kind of animal it is, right? So that's the goal that we're going to focus on. All right. Okay. So as stated, it is an ill-specified problem or under-specified problem, and often, it's not very meaningful unless you also assume something on top of it. Okay. So for example, what could be wrong? I could give you images of cats and dogs, and then I give you an image of a zebra. Ask you what's the label. Maybe you can say, okay, this is not a cat or a dog, but you might not be able to know what's the label, right? Because you haven't seen it before, right? Doesn't even make sense to ask or measure how good your prediction model is in that case. Okay. So we need to make some assumptions so that the problem becomes well specified. And the main assumption that is made in supervised learning, and this also plays an important role in many other learning settings, is that there is some connection between what we see in the data set, okay, and what we see or what we're being asked to predict on. Okay, so what are you going to predict on? It's somewhat connected to the data set that we see, right? If there's no connection, it's like saying, I'll teach you this entire course on algorithmic machine learning. You go to the final exam, and this PDE is there. We're going to do that, but that would be completely meaningless, right? So we don't want that. So you want some connection between what you're going to be asked to predict on and what you saw in the data set, right? So there is a ground truth. We don't know what it is often, but there is, at least the assumption is that there is a ground truth distribution on testing on, let me write it differently, on training and test example. Okay. More concretely, the assumption is that, so we have a distribution on X. The training data set, X1 through Xn, is sampled from X, and the test, or let's say sampled according to D. Okay, it's the same distribution for the training examples and for the test. Okay, this is the most important model. More recently, there's been a significant, sort of effort to understand out-of-distribution learning, what's called out-of-distribution learning, where you think there is some mismatch between the test and training data sets, distributions, and you try to characterize, okay, when can I still do something Or can I guarantee something even when I out of distribution settings and so on? But the most important constraint, or many of the important ideas show up in this setting. Okay. Any questions? All right. That's assumption one. So now it starts making some sense about the goal that we want to achieve. But we still need to make one more assumption. And after that, we'll kind of, get to really thinking of learning as just an optimization problem. The other assumption has to do with how are the labels connected to the training examples. Okay. So assumption one was just about the xi's. It said nothing about the y's, right? It said whatever the xi's was sampled from for the training, it's the same distribution for how the test sample is generated. Okay, but we did not say anything about the labels so far, right? But you have to make some assumption on the labels too, because if the labels are completely arbitrary, then you cannot make any prediction, right? Imagine, every picture is just kind of, random in some person, put this yi by, just tossing a coin. Then when I ask you to predict, you're not going to get a good performance, right? That even in those cases, you can come up with models, but it makes most sense to assume some kind of structure on how the labels are generated. Okay? The better way to think about it is to say, I'm not going to necessarily assume, sometimes we can make that assumption, but at the very least, let me assume what kind of algorithms or predictors I'm going to use. Okay, I'm going to limit the class of predictors that I'm going to use. Right? So okay. So the assumption two relates to, when I say, okay, predict the label for this example, you can make an assumption that, okay, the label is generated in some specific way. Or I tell you, okay, do the best you can when compared to this broad class of predictors. Okay. So that's, I think, a more robust way to do it. You can change what you're competing against and tell you, okay, this is what I'm competing against. Do the best you can if these are all your competitors. Okay. This, often what you're competing against is quantified in terms of model complexity. Right? So you're using a 10-layer network or something like that. That's the class that I'm working against. All right. Okay, with these two assumptions, we can now set up learning as optimization. All right. So meaning we have an underlying distribution d on x, right? And actually, it's even better to just say we have an underlying distribution on x and labels. And we have a class of predictors. So we have a class of predictors we are competing against. And the class of predictors we are going to assume are parametrized some way, right? So we have a parametrized hypothesis or predictor class. Okay. And just for notation, we will use theta to denote it. Okay. What's the format for this? It could be vectors, it could be discrete objects like decision trees, it could be a mix of the two, and so on. Okay. It could be a transform model, it could be a deep neural network, it could be a random forest, but all of those are parameterized hypothesis or predictor classes. Okay. So there's some parameters underlying the model that once you know those parameters, you can make the prediction. Okay. But we don't know what they are or what is the best set of parameters to use. And our goal is to figure out what is the best parameter or what are the best parameters. Okay. All right. So we're almost done. One missing ingredient is, what I just said. I said, okay, our goal is to figure out what are the best parameters or what is the best hypothesis to use. Okay. When I say best, you need a way to compare one predictor against the other, right? So we need a way to measure different, ways of making predictions. And the way to do that is by what are called loss functions. In what are called loss functions. Okay. So what is a loss function? It's just a function which tells you how good your prediction is. Okay. Maybe if you're doing like a classification task, your loss function could just be, okay, 1 or 0, depending on whether your prediction is correct or wrong. Right? It's a picture of a cat or a dog, and you say zebra, you'll get 0. Okay, your reward is 0, your loss is 1. Okay, but you can also imagine something more fine-grained, right? Maybe you're looking at predicting, the specific type of cat or dog it is, and you can kind of come up with scales, right? If it's a cat and you predict a different kind of cat, maybe you only incur loss of half. But if you predict a dog for it, maybe you get a worse loss and so on. Okay, so you can have all kinds of features for the loss function. And at this level, we're just going to keep it very general and just say a loss function is a function which takes one label and another label and compares how close they are to each other in whatever metric you want. Okay. It could be just like, okay, do they match exactly? Or if it's numbers, maybe it just says how close the two are and so on. Okay. Right. So it takes two labels, just two labels, and outputs a real number. All right. And with these things, we have a perfectly well-defined algorithmic problem now. There's no more ML. It's just an algorithmic problem. Okay, what do I mean? We have an input. Our input is the training data, x1, y1, x2, y2, and so on. Right? And what is our output? Or what is our desired output? We want to find a set of parameters such that, or set of parameters that minimize the cumulative loss of the corresponding predictor over your data set. Okay. Again, as I said, there are various ways to tweak it. For instance, you might penalize some kind of examples more than others. But let's just say at this level, as a starting point, we're just going to penalize every mistake the same way. Okay. So this means I have something like this. Right. So this is my loss function. This is my predictor with parameters data. Okay. So I'm just looking at the training data so far. So looking at the training data, come up with the best set of parameters, best set of weights, best set of decision rules or whatever you have, such that for each example xi, my prediction is as close to the true label or the label that I see in my training data set as measured by the loss function that you picked. Okay. So if you pick the loss function L and the parametric representation, this is now a well-defined problem. Okay. So we have this input, we want this output, and the whole question is what time complexity, what resources do you need or to compute this thing or that minimizes this, or at the very least, get close to the minimizer. Get close doesn't mean you're getting close, doesn't necessarily mean getting close to the true set of parameters which minimizes it, but just minimizing this overall loss. Okay. Both are related, but you can take both forms. All right. Any questions about this basic setup? You're going to work on this specific optimization problem a lot. So if you have any questions about the motivation for it, let me know. Okay. And this number is really called the training loss. Okay. So note that, to define this problem, assumption one is kind of not playing a role, right? So the, given any training data set, I can define this optimization problem and try and solve it. But to connect it to what you would do on a new example, you need some assumption like assumption. Okay. I minimize this. What do I see in the future? If it's not connected to my training data, then I cannot make any guarantees. Then I cannot give you any guarantees. Okay. And this is called, there's a very specific name, what we wrote down. This algorithmic problem is called empirical risk minimization, or ERM. Okay. All right, so we're just doing this on the training data. And if you're, if you want to know more, the training data, whatever you're minimizing on the training data is really kind of a surrogate for minimizing it under the true distribution that we want to solve it on. Okay, so imagine someone, there's some underlying distribution on the examples and their labels. I can ask, okay, find me the predictor which achieves the best performance under that distribution. Okay, but we don't have access to the full distribution. That is often too much to hope for. But what we have access to are samples generated from this distribution. Okay? Can imagine that whole of text that we see is coming from some quote unquote natural distribution, but no one knows what the distribution is. But what we do know is that we have many, many samples generated from that distribution. Okay. So that's why this is called empirical risk minimization. If you write something like this is called population loss. Meaning, imagine you have an infinite number of samples, then you would arrive at this. And what you observe here, this is called empirical loss. This is the loss that I estimate our model will have based on the training data that I have seen. Okay. All right. And just as a remark, there is a whole field called statistical machine learning. And one of its main goals is to connect empirical loss to population loss. Okay. So, even if I tell you how to minimize this, it doesn't mean you necessarily have a good predictor. Somewhere, that's the statistical machine learning part. That's about the modeling part, which we are not going to cover. Okay. Many cases, they both go hand in hand. Sometimes the only way you can show some kind of conversion from empirical loss to population loss is by coming up with an algorithm in the first place. Okay. But this is a step, it's very beautiful many times, but something that we are going to completely ignore for this course. We're only going to focus on solving this box. Okay. Any questions about this so far? Right, so far very generic, but we'll get concrete pretty soon. We're looking at examples for ERM and how to solve it, and that's going to be the topic for let's say the next 3 or 4 lectures. Okay. All right. To summarize, where are we right now? We can forget how you came up with the loss function, what's the prediction hypothesis class that you're using, and just focus on this problem. Yes, so how to solve ERM. Okay, that's what we're going to focus on, right? So let's do a couple of quick examples to kind of understand, what kind of choices we have for picking these parameters, for picking the loss functions, and so on, right? The simplest and I would say maybe still the most used across various sciences is linear prediction. Okay. So here, a domain is going to be modeled as d-dimensional vectors. So each example x has d coordinates. Okay. And our label class is just real numbers. We're not looking at classification like 0 or 1, cats and dogs, but just real numbers. Maybe it's about predicting what's the temperature going to be tomorrow or something like that. Okay. And lastly, we have to decide what's the predictor class. I guess not the last thing. We also have to decide the loss function. But the predictor class that I'm going to look at is also determined by d-dimensional vectors. Okay. As I said, this is just an example, one of the simplest examples, but still very useful to think about. Okay. And how is the prediction made? It's a parameterized class. So given some parameters theta, I have to tell you what is the prediction. And the prediction is just the weighted sum. Right? So it's theta I times. Okay, so just to expand it out, it's theta 1 times x1 plus theta 2 times x2 plus so on. Okay. You can imagine, maybe each feature in my example has some attribute, right? If it's about predicting the temperature, maybe each feature is like, whether was there rain yesterday or not, or is it windy, maybe about the temperature yesterday and so on. And you're trying to make a prediction for tomorrow, right? And depending on the features, you want to give them different weights, multiply the features with that, and then add them. Okay. And for short form, we will throughout use this inner product notation. Okay. So this is notation for the inner product between two vectors, which is just this product, this sum, right? Okay. So we have the domain, labels, predictors defined. What's missing is the loss function. Depending on the loss function you choose, the ERM can change significantly. And sometimes it can make it harder or, easy also. Okay. And one of the simplest loss functions to use is the squared loss. Okay. So this just measures how close the two predictions are, the two labels are. Okay. And we want it to be non-negative, so here is just a square. All right. So what's the corresponding ERM now? So someone gives me as input x1, and once I start writing vectors, I'm going to switch to superscripts for the training data label so that we don't get confused between the two. Okay, so we have n training examples, and each xi here is d-dimensional, and our output is supposed to be find theta to minimize the total loss, which is just the cumulative loss across the different samples. Our definition was okay. Okay, so why is this? So we really want the ERM problem. We want to minimize the loss between what we predict and what was observed, right? So which is just the loss is the squared loss, so you end up with this problem. Okay. And there's a name for it. Does anyone recognize it? I'm sure some of you have seen it at least. Yeah. Least squares regression, right? So this is least squares regression. Okay. As you'll see, this is a long, very, very well studied problem. We kind of know everything there is to know, or, for the most part about this problem. But nevertheless, we're going to start with it because, as we'll see, it's a very good example to develop algorithms, which can then be extended to all kinds of other powerful models. Okay. And the intuition that, the algorithms that were developed for this model are used extensively for all of the modern machine learning tools too. Okay. It doesn't mean there are no new ingredients. In fact, you have to add a lot of new ingredients, but these basics are very important. That's where you start. Okay, that's what we are going to cover. How do you optimize it? What are the best ways to optimize it, and so on. All right. And of course, you can now start changing stuff, right? So as a second example, in the same context, let's say I have all of these things the same, and I say, okay, change the predictor class. You can, or I can also just change the loss function, and that can change the problem significantly, right? So maybe I'll have all of these exactly the same, except I'll put okay, absolute value of image, right? And then that gives me a new ERM. Okay. The thing to keep in mind is that when you think from like an algorithmic perspective, it does really look like a very different problem in some aspects, but also very similar to the other problem, right? So the prediction class is similar. Does changing the loss function alone make a significant difference? It can. Okay. In fact, the optimizers could be very, very different, and even the algorithms might have to be extensively different. All right. And I could also do something like this. Well, hmm, can you imagine in some applications, maybe you don't want arbitrary sort of linear predictors. Okay. You might want only predictors where somehow the weights are positive. Makes sense. Let's say based on your past grades, you're trying to predict the next grade. Maybe if you do well in some course, maybe your chance of getting grade increases, but you might say the weights should all be positive. Okay. That's a new optimization problem. Okay. And the only thing that changed there is the class of predictors in some sense. Okay, wrong thing got pasted. So let me undo that. Okay, so everything is the same, except now I say the predictors are all vectors with non-negative coordinates. Okay, this could be an important constraint in some application. Like you want some interpretability, what these theta i's are, or in some cases, those are the only things that you care about. Right? And then you can write down the same optimization problem, like here. Okay, so I should say this greater than or equal to just means that all coordinates are non-negative. Yeah. I mean, that's up to us, right? So all we are saying is this is the optimization problem that we have to solve. Meaning, give me the theta which has non-negative coordinates and gets the minimum possible loss among all predictors with non-negative coordinates. Right? So we reduce the class of things that we're competing against. So we should do much better potentially, right, to the best predictor in the class. But it's a little bit counterintuitive, but sometimes when you restrict the class of predictors, the problem gets harder. Right? Least squares regression is easy to solve. What I wrote down here, this is basically linear programming. It's much more powerful. Okay? So just by changing the prediction class, you just encoded one of the most important algorithms in, not just machine learning, but computer science, which is linear programming. Okay? So just what theta you choose, what loss function you choose can have big impacts on what kind of optimization problems you're solving. Right? So that's why I said, often it's an important sort of skill to pick the right model and the loss function that has enough expressibility, but also optimizability. Right? We are separating the two completely, but they should really be done together, when you get into it. All right. You don't need to know why this connects to linear programming, but just to say this is a much, much harder problem than least squares regression. Okay. Any questions about what kind of things that you might end up with by setting up ERM in different ways? Okay. So given that changing the loss function, changing the hypothesis class, you end up with completely different problems. Do you have to come up with new algorithms every time you have such a change? Okay, that's the main sort of biggest sort of nightmare scenario for computer scientists or any person designing algorithms, right? Which is to say you have to start from scratch every time. That would be very unintuitive and not very useful. Okay. Luckily for us, there are at least a few algorithms which are broadly applicable across many of these loss functions, many of these parametric classes, as long as you can do something which you can precisely define abstractly with those classes. Okay. In some cases, they give you the best results, like least squares regression, we'll see, can be solved in various ways, even by these meta algorithms which work across all kinds of optimization problems like this. Linear programming, when I put this greater than or equal to 0, requires more effort. Okay, but you can still approach it in this way. All right. Okay. And there are also very important loss functions that other loss functions that people look at. Like if you're looking at classification problems, there's something called hinge loss. There's also something called 0-1 loss. And I'll define them when we are looking at examples later on. Okay. All right. So I'm going to further abstract out what we're doing, even move away from ERM here. Okay. So if you think about what we are doing here is I have some function L of theta, right? The parameters are coming from some RD, and my goal is to minimize this loss function L. Okay. So let's just focus on that. The loss function itself has a specific form, which is the sum of these individual loss functions evaluated in the training data set. But let's not worry about that for a little bit. Okay. We'll come back to that later on. So I'm going to assume that we have some loss function, total loss function L, which takes some set of parameters and tells you how good this model is, or this set of parameters are. Right? And our goal is to find theta to minimize L of theta. Okay. And we're also going to look at what's called unconstrained optimization. Okay. So unconstrained optimization refers to the fact that I'm not, for the time being, allowing any further constraints on where these parameters can come from. Okay. Unlike example 3, here I said, okay, the set of parameters must be non-negative, right? So I'm simplifying it more and saying all parameters are allowed for now. Okay. Does that make sense? And there is a way to kind of switch between the two without too much difficulty, because you can have a scenario where I put some big penalty for having a negative coordinate. Right? So that would be one way to enforce sort of positivity just from a single objective function. Okay. So we're going to focus on unconstrained optimization. I have some loss function L. We'll figure out what kind of access we have to this cumulative loss function L, and our goal is to pick or find a point which minimizes this loss function. Right? At the very least, if I can solve this problem effectively for all L in some reasonable space, then it should be useful for ML, right? Because it's exactly what ERM is. Okay. Okay. So let me draw a picture, and that will lead to our first sort of algorithms, right? Let's imagine, this is a picture in one dimension. Obviously, we're working in high dimensions when we're doing the optimization. But let's say for now that my loss function is just L of theta, it's one parameter model, and the loss looks something like this. Okay. And from the picture, you can see maybe this is a point which minimizes the total loss. Okay, so we want to find this point. And we are going not some of the power of the algorithm that we're going to develop. In fact, the most of the power comes from the fact that it's a simple enough algorithm. It's going to be slow in some sense, not as fast as you can probably achieve if you had full access to the loss function. Okay, so we're going to assume that we have some kind of limited access to the loss function in terms of local evaluation. Again, this is a vague term, but it will get precise as we go along. So one natural algorithm for trying to, so let's say what would be a natural way to try and minimize this loss function? I'm at some point here, I pick some random set of parameters and then say, okay, is this good or not? Right? If it is not good, maybe I try and improve the set of parameters some way. Right? So the basic idea is pick a starting point and move in a direction that reduces the function value. For this part, it's not important that it's actually a loss function from ML or anything. You can just think of it as an arbitrary function that is given to you. Okay, so like let's say I'm here. Okay, you look at it and say, when I move a little bit to the left, my function value is increasing. When I move a little bit to the right, my function value is decreasing. Okay, so that's the kind of local axis that we're going to assume we have, right? A little bit to the left, it increases, a little bit to the right, it decreases. So since I'm trying to decrease, I should just kind of, move in this direction. Okay, but you can, even from this picture, you can see it can backfire because when I'm here, the true minimum is here, but if I use this local rule, I'll go back here. Okay, but it's one approach, and we'll see what it gets us. Okay, and as simple as this idea sounds, it's a very important one. So the idea is move in a direction that reduces So what does this mean? Maybe in 2D it's always, there's no ambiguity, but imagine you're actually, think of the loss as some, landscape, right? It's really mountainous valleys and mountains everywhere, and you're trying to go to the deepest valley you can. And this is in our regular 3D space. You're lost in the Himalayas, and you want to go to the bottom of the mountain, okay? And wherever you stand, you can make this local thing. Okay, if I move this direction, is the height increasing or not, right? And you want to go in the direction that decreases your height. But in 3D, there can be very different directions which all decrease your height. Right? If I'm on a valley, if I'm looking down, even if I go in this way, effectively my height is decreasing. If I go straight down, also it's decreasing. If I go a little bit diagonal, also it is decreasing, right? If you go, you can either do switchbacks or you can just cut straight through, right? So both of them decrease your function value or height. Now the question is, which one would you pick? Don't think, in terms of safety. If you are just a fast skier, what would you do? The steepest one, right? You just go straight down, right? And the reason I'm emphasizing this is people have figured out how to play even with this little bit of intuition, okay? More specifically, so what you're asking for is move in the direction that gives you the most bang per buck, meaning move in the direction that gives you the most decrease in function value compared to the distance that you move. Locally, like, within some short distance, if I move 1 foot, my function value decreases by 10 here. If I move 1 foot in this direction, my function value decreases by 100. So I should pick the 100 direction. Again, we're being very greedy, very local, right? We're not looking way, far ahead. We're just saying right now, what is the direction that gives me the steepest possible decrease? Okay. And calculus 101, if the distance that you use is Euclidean, okay? Remember, we're working in abstract space, right? In the real world, when you think of like being lost in the mountains, then you're just looking at literal distance, which is Euclidean distance, right? In the abstract space, you can imagine all kinds of different distances. You can say maybe you're working with some kind of total variation distance, if you know what that is, in probability space, or all kinds of crazy distances exist, right? You can ask, okay, in that distance, which direction gives me the most bang per buck? That would be a very different question based on what distance you use, okay? But by and large, the distance that most people use is Euclidean distance, okay, which is, suitable for many applications. If not, you have to massage the problem to make it suitable, right? As I said, often these two things go hand in hand. Algorithms versus the modeling. When you separate the two, we're going to focus on sort of making some simplifying assumptions here, okay? So we're going to assume if the distance is Euclidean, meaning that what you're asking is, okay, what is the direction that gives me the most bang per buck in terms of distance moved? And the distance is measured in terms of Euclidean distance, meaning given any two vectors, these are two vectors in RD, the distance squared is, look at each coordinate, how far they are, sum of squares of their differences. Okay. If the distance is Euclidean, then the direction of steepest distance is, okay? So calculus 101 tells you the answer to this basic question of what is the most, which direction gives me the most bang per buck? What is the direction which gives me the steepest descent? It's the negative of the gradient of the function at that point, okay? So just to write down the gradient formally, we're going to assume our function is differentiable for now. There are also extensions to other cases. So we have this function from RD to R. Then the gradient of the function at theta is just a d-dimensional vector, which is a set of all partial derivatives. Okay, so this is the d-dimensional vector. And as it happens, you can compute the direction of steepest descent just by computing the gradient. All right. So in some sense, the only access we are going to assume about the loss function or this function that we're trying to minimize is that we can compute its gradient. Okay, that's the simplifying assumption that I said we'll make. That we don't necessarily need to have complete access to what the loss function L is. As long as you give me the ability to compute its gradients, I can do this specific optimization. Or at least I can try this specific optimization. Right? So this leads to a very simple but extremely important algorithm for modern machine learning, which is just gradient descent, or GD from now on. Okay. And you pick the starting point. Theta 0, some way, you might be clever about it. You might just use random initialization or what have you. Okay. And then for different steps, you just set you take a step along the direction of steepest descent. Okay. But you're a cautious person, so you don't kind of go way too much along this direction of steepest descent. You take a small step. Again, this is a tunable parameter. It's called the learning rate, step size, whatever. Okay, or also called the learning rate sometimes. Okay, it's one of the more important hyperparameters. Any questions about the setup? And this is gradient descent, but if you change how you measure the distance, you do get different versions of gradients. The gradient or the direction of steepest descent might be more complicated to compute, but it might be more useful for some applications. And in fact, that's one of the ways that people discover really, really important algorithms. Okay, by changing how you measure the distance and so on and so forth. Okay. Any questions about this? All right. So let's do an example of least squares regression. Where did it go? Okay, so this was a problem, least squares. This was a problem of least squares regression. How do you solve it? Well, we can apply gradient descent. And if you want to try gradient descent for this, we need to know what is the gradient of the function. Okay. And by now, almost every ML package has tools to compute the gradient directly for you. Right? There's Autograd and all kinds of tools to do it. And for this one example, let's just work through it slowly. Okay. The reason computing the gradient of the seemingly complicated function is easy is because gradient descent is a linear operator. Meaning, if you think of it as the sum of different functions, then the gradient of the sum of different functions is just the sum of the gradients. Okay. So this is again, calculus 101 is gradient of these little things. Okay. And I'm not going to do this derivation. Let's say this is calculus 101. Just have to apply the chain rule and you get this expression for the gradient. Okay, and this is based on chain. Okay, so chain rule tells you that if I want to compute the gradient of this function, I can think of it as a composition of two functions. One is basically computing the inner product, and one is computing the square. So you first compute the derivative of the square, and then compute the derivative of the inner product function. Okay, but the punchline is that we have a very simple algorithm for computing the gradient. It's just this summation, right? So this leads us to GD for least squares regression and a simple algorithm. Okay. Any questions? All right. So that's the first example of gradient descent. And let me do another example because that will motivate something slightly more general. This was another empirical risk minimization problem that we wanted to solve, right? Well, how can I solve this? I can still try and use gradient descent. But what is the gradient of this function? Can I compute the gradient here? Well, not really, because this function is not differentiable. Okay, so absolute value, now this is absolute value of something. So even if I take one dimension, then absolute value looks like this. So it's not a smooth function. At 0, it kind of just arbitrarily changes its direction, right? So kind of this pointy function, so it's not a differentiable function. So how can I apply gradient descent for these sorts of functions? Well, you can still do it by something called the subgradient. Okay, so subgradient is a direction G is a subgradient if okay, so a subgradient is basically defined something like this. So let me take the absolute value function as an example. So this function, it doesn't look like absolute value, so let me redraw it. Okay, this is the function y equals absolute value of x. Okay, it's not differentiable at 0. Okay, so it's not differentiable here. Okay, and it seems like an annoyance, but I should tell you that this absolute value or the closely related ReLU, which is max of 0 comma x, is used everywhere in modern machine learning. Okay, and this function is not differentiable. So how do you use it for gradient descent? Okay, point is that you don't need too much to at least make some progress in gradients, or at least basic theory to apply. and it tells you what you need in terms of what's the right direction to choose. Okay? It's differentiable almost everywhere except here, right? So what you can do instead is you really say I can pick any direction as long as the corresponding sort of line that I draw is below the curve. Okay. So one of the geometric views of gradient is that if I take a curve like this, then the gradient is really the slope of the tangent line. Okay. So these tangent lines give you what the gradient is. The slope of these tangent lines give you the gradient, right? And what is the geometric property of the tangent line? Geometric property is that around this point, it only intersects the curve at that single point. Okay. So it might intersect the curve back again here, but around here, it doesn't touch it again, right? So that's the definition that you can lift to non-differentiable functions. Okay. Okay, subgradient G, if a direction G is a subgradient of F, if okay. So I'm not going to define it formally or how to compute it, but suffice to say that there's a simple way to extend it even to non-differentiable functions. And as I said, this is not just a curiosity. In fact, the subgradient descent is really the one that gets used the most because of functions like uh, okay, so this is my function. It's basically 0 here, and then it becomes like this. Okay, so it's not differentiable. So how do you deal with it? You use subgradient. Okay. All right. So you don't need to know exactly what it is, but you know that, just keep in mind that there is a way to extend it to non-differentiable functions as well. And once you do it, the subgradient descent algorithm is similar. Okay. Take any subgradient at theta I minus 1 and take a step along that direction. This is subgradient descent. Okay. All right. So, it's a simple enough algorithm, and it has some big advantages. And as we'll see, you can still some big advantages in terms of what is needed to optimize it or to run it. Okay. In particular, I would say the biggest advantage over many other algorithms is that we only need to be able to compute. Okay. So imagine someone tells you, okay, the loss function, you don't even know what it is. All I tell you is every time you press a button, I'll give you the gradient of the function. That's it. Okay. Give me some theta. I'll tell you the gradient of the function at that specific value. That's the only access that you have to the function. There's no sort of way to look into it and see, okay, this is how it's being computed or anything like that, right? Even then, I can run gradient descent. Okay. And that's one of the main reasons it's so useful is because you can assume, you can run it with so little information about the function. Right? So it's applicable across many, many different functions. Right? And such functions which only use information about the gradients and nothing else are called first order methods. Okay, so just as you're only assuming information about gradients, you can also look at second order methods, which assume I can compute all kinds of second derivatives, Hessian, and so on of the functions. Okay, they can run faster in kind of finding the minimum, but they need more compute power for each iteration. And sometimes you might not even have that information to run them. Okay. So as far as algorithms to try go, gradient descent is one of the most minimalist algorithms. What it gets might correspondingly take a hit, but at the very least, it's very broadly applicable. Okay. All right. So let me say one last thing, and then we will resume this discussion next lecture. So GD for ERM. So remember, our machine learning problem was basically we're trying to minimize this function. Okay. Now, to run gradient descent, I need to be able to compute the gradient of this function. And as I said, the gradient is a linear operator. So it's just gradient of this guy. Okay. And I can use the chain rule to compute this. Okay. And this is, think of L as a bivariate function, and I'm computing the partial derivative with respect to the first coordinate, right? So this kind of separates how L and H interact. This is by the chain rule. I just need to be able to compute the first derivative with respect to for the loss function, and then the gradient of my model at theta. Okay. So as long as I can do these two things, I can run gradient descent on whatever model you have. All right. And what we're going to do over the next few lectures is to figure out, all kinds of things about gradient descent. Does it run well? When does it run well? Will it run well no matter how I choose this step size eta? Okay. And even among first order methods, let's say I tell you that you're restricted to only first order methods. You can only access gradients and nothing else, either because computational resources or memory resources, or maybe that's all the thing that you know about the model. Okay. In those cases, is GD the best possible? It's not. In fact, there are much better algorithms, as we'll see as well. Okay. And if you think about why we are doing this, I should say by now you can code up any model and just say optimize, and it'll run gradient descent, figure out what the best parameters to use are, where to start, what are the step sizes, and everything, just in the package, right? But the reason I'm assuming you came to this class is not to use the tools, but to open them up and potentially build better tools when needed, right? So if you don't know how these basic things are running, how are you going to improve them? Okay. So learning these fundamentals are important for that reason, not because, these are, the first time you'll be able to run gradient descent. You can run gradient descent without knowing how it works very easily, right? But if you want to improve it, or maybe some reason you have to tweak it later on, you need to know how it functions, okay? And so that's why we're going to look into the theory behind gradient descent, like where does it come from, what kind of rates, how fast does it get to this optimum? When does it get there? What kind of tricks can I do when it doesn't get there? Can I speed it up somewhere? Can I accelerate it? And so on, okay? So those are the questions that we'll try and understand. As I said, not because this will help us immediately use gradient descent, that you can do without knowing anything. A 10-year-old can do that now, right? But they potentially cannot open the black box and build something better with it, okay? All right, so we'll talk about that in the next lecture, all right?